Today's lecture is about the ideal gas law and vapor pressure. The ideal gas law is useful for a number of things, mainly for determining the density of gases. We talked about with liquids, density is fairly predictable and doesn't change much with pressure or temperature. That's not true with gases. With gases, the density varies quite a bit depending on conditions, and with gases you wouldn't want to look them up on a table. You'd want to use the ideal gas law to figure out what their density is. And it's stated like this: pressure equals the density times R times temperature. Now when I learned this in high school, I used, this was the formula I was familiar with, PV equals nRT, pressure times volume equals N, which is usually the number of moles, times R times temperature. And if you rearrange that, you can see N over V is really a statement of density. So these two formulations are consistent with one another. Just wanted to point that out before we went on. So let's talk about these different variables in the equation. P is for pressure, and that's the force per unit area. And there's lots of different units you can use for pressure: atmospheres, torr, millimeters of mercury, kilopascals, psi. Kilopascals and psi are the most common units used in either the metric or the English system. R is the ideal gas constant, and you can look this up for different fluids. Every fluid will have a different number for this, and it won't change at different temperatures. It's constant for the fluid. But be careful of the units. There's this constant is used in all kinds of different equations, and you will have very different units depending on what textbook you look at. In our textbook, it's set up for the ideal gas law, so it's in the appropriate units, and there's what the ideal gas constant is for air there. And then the last variable in that equation is temperature. It's got to be in Kelvin or degree Rankine if you insist on using the English units. Kelvin, you know, is Celsius plus 273, and Rankine is Fahrenheit plus 460. So these are both relative to absolute zero. We have to define a few things about pressure before we work with it. Pressure can be defined based on different 0 points, different datums. The first type of pressure is gauge pressure, and this is where you assume that pressure is 0 at atmospheric pressure. And this is what we typically work with and what most gauges read. If you're reading a tire gauge and it says 0, that doesn't mean that your tire has a vacuum and it has the pressure of outer space in it. It just means that it's equal to atmospheric pressure. So gauge pressure is what's most commonly used. But sometimes we need to consider the absolute pressure, and this is the pressure relative to a vacuum. When we talk about atmospheric pressure, for example, we talk about it being 14.7 psi, and that is the actual pressure that our body is feeling from the air around it, and it's relative to the vacuum of outer space. So if we think about these two different number lines for gauge pressure, atmospheric pressure is 0 psi, and the lowest pressure you can get is the vacuum of outer space, which would be on average minus 14.7 psi. If you report the same thing in absolute pressure, at atmospheric pressure it would be a positive 14.7 psi, and outer space would read a pressure of 0. So with absolute pressure you can't have a negative pressure. With gauge pressure you can have negative pressure, which is referred to as a vacuum. And we can convert from one of these to the other, where the absolute pressure is just equal to the gauge pressure plus whatever the atmospheric pressure is. And so you need to be familiar with these two different things, gauge pressure and absolute pressure, and be able to convert from one to the other. It can be fairly confusing. It's not always clearly stated exact if you're using gauge pressure or absolute pressure. One clue is with English units. You can use these units of psi-A or psi-G, where the A refers to absolute and the G refers to gauge. So that's just PSI, but the A and the G tells you what kind of pressure it is. There's no equivalent to that in metric units, and otherwise you just have to figure out whether they mean gauge or absolute pressure by context. This is true in the textbook, and it's even more true when you get out into the field and you're working with different types of equipment. So let's look at these examples. A tire gauge reads 59 psi. Most gauges are going to report gauge pressure. So if we use our conversion equation there to go from absolute to gauge, our gauge pressure is then psi, because that's what the gauge reads, and then the absolute pressure would be 73.7, or 59 plus 14.7 psi. 14 psi is sort of average atmospheric pressure at sea level. It does change depending on the weather. Okay, a tube had a vacuum of 5 psi. Vacuum means that it's below atmospheric pressure. So, but that is a gauge, so this is a gauge reading of -5, and using our conversion we can convert that to an absolute pressure of 9.7. Atmospheric pressure today is 13.8 psi. Whenever you're working with atmospheric pressure, you want to report that as absolute, so that is an absolute reading. And then the gauge pressure would be 0, because to convert from absolute to gauge, you subtract off the atmospheric pressure. My scuba tank was down to 500 psi. That's a gauge reading, so it's 500 gauge, and that would be an absolute pressure of 514.7. Okay, let's do a quick example. Say we've got a helium-filled blimp of a certain size with an internal pressure and a temperature. Atmospheric pressure is also listed. I'm asking to find the density of the helium inside the blimp. So we would use our ideal gas law. I'm solving for density, so I'm going to rearrange in that format. First thing I'm going to do is get my textbook and look up the ideal gas constant for helium, and that's 2077. I then need pressure and temperature. Pressure is given as 50 kilopascals. That's a gauge pressure. For the ideal gas law, we always have to use absolute pressure. So I have to convert that from gauge pressure to absolute pressure. So that's 151,000 pascals. And then temperature needs to be in degrees Kelvin, so I need to convert that. And now I've got all the pieces, and I just have to plug it all together and punch it into my calculator. Notice that the units work out because you have joules on the bottom and a Newton meter on the top, and those are the same, so that does cross out. So you're left with a density in kilograms per meter cubed. Okay, that's the ideal gas law. It's pretty useful. We're going to now talk about vapor pressure. This is a strange property of fluids. If you take a container with water in it, and then above the water is air, but it's dry air, so there's no, there are no water molecules floating around in the air above the water. You let it sit for a while, and what you'll find is eventually there will be a bunch of water molecules floating around up there. So how do they get there? As you know, liquid molecules are always in motion, and they're moving around over each other. Occasionally a molecule will attain enough energy that it can break free of the solution and go shooting off into the gas. But in the same manner, the gas molecules which are flying around, every once in a while they collide with the liquid and become part of the fluid. So there's this interaction of liquid molecules breaking free into the atmosphere, and then gaseous molecules colliding and joining the water again. And this equilibrium is controlled by intermolecular forces in the liquid, and it varies from liquid to liquid. When these processes reach equilibrium, you will be able to count a predictable amount of water molecules above the water, and that's what we call the vapor pressure. Each fluid has a unique, or has a different vapor pressure, which you can look up. Another way of looking at this is, let's talk about boiling. So if you take water at 20 degrees Celsius and you heat it up, eventually it will start to boil, and we all know that boiling occurs at 100 degrees Celsius. That's actually not the best way to describe boiling, though, because if you go up to Denver, if you're up at higher elevation, boiling occurs at a much lower temperature. So how can this be? How can you have water boil at a low temperature? Temperature is actually not the best way to describe boiling. So let's talk about this a different way. When you start with water at room temperature, it has a vapor pressure of 0.23 psi. As you heat it up, you change the vapor pressure in the water. Vapor pressure is dependent on temperature, and as you heat up the water, the vapor pressure rises until it reaches 14.7 psi. And then boiling actually occurs when the vapor pressure exceeds the atmospheric pressure. So that's a better way to understand boiling. And in fact, you can even get liquids to boil, you can even get water to boil at at room temperature if you were able to just drop the pressure really low around it. And here's an example of getting a liquid to boil just by reducing the pressure and not changing the temperature at all. This is interesting. We can also now talk about cavitation, which is an important problem that can occur with different machinery. So you can get water to boil by dropping the pressure around it. This can happen not just at the air-water interface, but underwater as well. If you drop the pressure in a fluid below the vapor pressure, cavitation will occur. And what happens is you actually get the water to boil. The liquid vaporizes and forms gas bubbles. This can be very destructive. These bubbles form and then they rapidly collapse, and those implosions can really damage equipment. Note that the pressure that you have to compare the vapor pressure to has to be the absolute pressure, not the gauge pressure. Here's some pictures of cavitation occurring around a propeller. You can see streams of bubbles coming off of the tips of the propellers. You can also see bubbles forming along the blades themselves. Those are all cavitation bubbles. And the reason why is because you get very low pressure developing along those blades. We haven't talked about this yet, but when we talk about Bernoulli, what you'll learn is that when you increase velocity in a fluid, you correspondingly decrease pressure as well. So in these systems where you have fluids moving at very high velocities, you can generate very low pressures. And in this case, low enough to drop below the vapor pressure and cause water to boil. You have to beware of cavitation. It can cause a lot of noise and it can cause a fair amount of damage to the equipment. Here's an airfoil where you can also generate very low pressures along the top of the airfoil. This airfoil is underwater and you can see the water boiling above it as a result of that low pressure. So we looked at two different things, two different apparatus where this can happen with propellers and airfoils, but you can get cavitation in any system where you get a low pressure to develop. So when you see cavitation in problems, just remember you have to compare the actual water temperature, the actual water pressure in absolute terms. You have to compare that to the vapor pressure of the fluid, and if the absolute pressure is below the vapor pressure, you will get cavitation.